In this video, we will talk about what we mean by orbital hybridization as it pertains to the valence bond and molecular orbital theories. As a quick review, valence bond theory uses the idea that chemical bonds occur through the overlap of those quantum mechanical orbitals that we dealt with when we were talking about electron configurations. One of the issues that arises is that the number of partially filled or empty orbitals do not predict the number of bonds or the orientation of the bonds. If we look at carbon, whose valence electrons, we have two occupying the 2s orbital and then two p orbitals. So we could say that one is in the px and one is in the py, and then the pz is completely empty. From this, we would predict that two or maybe three bonds that are 90 degrees apart should be observed rather than what we would see for like methane, where four bonds are 109.5 degrees apart. To adjust for these inconsistencies, it was postulated that the valence atomic orbitals actually could hybridize, which is a form of adding the forms of their wave functions together before bonding took place. So one hybridization of carbon is to mix all of the 2s and 2p orbitals to get four orbitals that point at the corners of a tetrahedron. Pictorially, the problem, as described previously, is if we want to bond together hydrogen atoms with carbon, our carbon has the 2s orbitals fully filled, and the 2p orbitals, only two of them are half filled. From this, we would expect, because we're interacting p orbitals, which are linear in nature, with our s orbitals, the p orbitals lie directly along the axes, and so what we should see is a 90-degree bond angle. But when we're bonding carbon with hydrogen, we get methane, CH4, so we would get four bonds as opposed to the two that would be predicted by looking at the electron diagrams. We get four bonds, and the angle is 109.5. So we have to do some sort of mathematical addition of the orbitals to get what we will be calling hybridized orbitals. Hybridization occurs through the summation of multiple valence orbitals. Some atoms hybridize their orbitals to maximize the bonding. The more bonds, the more full orbitals that are hybridized together, the greater the stability. Hybridization is the mixing of different types of orbitals in their valence shell to make new sets of degenerate orbitals. Degenerate meaning that they have the same amount of energy. The examples that we will be using are the sp, the sp2, the sp3, the sp3d, and the sp3d2. What the name here implies is the orbitals that are being added together. So in the case of the sp, you're adding one s orbital with one p orbital. The sp2 is taking an s orbital and adding to it the functionals of two sets of p orbitals. Then we have the sp3, which is adding together the wave function for one s orbital and three of the p orbitals. The sp3d is taking one s orbital, three sets of p orbitals, and the wave function for the d orbital, and adding them all together, combining them to come up with new hybridized orbitals. And then the sp3d2 are an addition of s, three sets of p's, and two sets of d's, all mixed together to come up with the hybridized orbitals. What a hybrid orbital typically looks like is if we imagine a p orbital and add it to the spherical s orbital, the result is, because your p orbitals have a plus end and a minus end, and the s orbitals are all one, where they add together, the wave functions constructively add, and the orbital on that side gets bigger. You get a constructive interference. On the other side, where the orbital of the p would be negative and the s would be positive, when you add the two together, they subtract, or they undergo destructive interference, becoming smaller. So you get something that ends up looking somewhat like a p orbital, but it has one lobe that is very large, where you have the constructive interference, and one lobe that is very small, where you have the destructive interference. The same type of atom can have different types of hybridization. Carbon, for example, is very common to see sp, sp2, and sp3 hybridized orbitals. A key feature to remember when you are first learning about hybrid orbitals is that the number of standard atomic orbitals, that would be your s, p, and d, that you are adding together equals the number of hybrid orbitals that are formed. So for example, carbon, we could combine one of the two s orbitals and three of the p orbitals, or three of the two p orbitals, gives 4 sets of sp3 hybridized orbitals. Hydrogen cannot form hybridized orbitals because its valence shell only has one orbital available to it, which is the 1s orbital. So looking at carbon, we have the 2s orbitals, which are lower in energy, and then we have our 3 p orbitals, which are degenerate. They all have the same amount of energy. Looking at our electron diagram, how the orbitals are being filled, for an individual carbon atom that is not participating in bonding, our 2s orbital is completely filled, and the 2p's have one electron in 2 sets of the 2p's, and one of the remaining 2p's is completely empty. When we hybridize them together, because we are adding all the different wave functions together, we end up with the same number of wave functions coming back, but all of those wave functions have the exact same energy. Because they have the same energy, they will follow along with the same rules that we were using when we were filling our electron diagrams. They're all the same energy, and so we populate them first with all the electrons being spin up. So you half fill all of your orbitals before you start putting a second electron in any one of your orbitals. So because carbon had 4 electrons to start with, it has 4 electrons to finish with. And because we are hybridizing 4 orbitals, we get 4 orbitals back. So for carbon, it has 4 orbitals, each one having 1 single electron in them, meaning they can easily form 4 bonds. The number and type of standard orbitals that combine together determines the shape of the orbitals, determines the shape of the hybrid orbitals. The particular kind of hybridization that occurs is the one that yields the lowest overall energy for the molecule. In our next videos, we will be looking at what those hybridized orbitals look like and the resulting shapes that we get when we start hybridizing different combinations of our standard atomic orbitals.